span of a set. Suppose you have a set like S, V1, V2, V3, Vk, which is a set of vectors in a vector space like V. Then the span of this set is the set of all linear combinations of the vectors in S. So again, here you have a set with some vectors in it. You're going to take all possible linear combinations of the entries of the vectors in that set, and you're going to call it span of S. C1 V1 plus C2 V2 plus dot 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 plus CK VK, and CI's, they are all real numbers. The span of S is denoted by a span S or a span. We're going to list the vectors that you're using to create linear combinations. When span of S is the same as vector space V, it's said that V is spanned by these vectors. Or another terminology is that S, this set that you have here, basically spans the vector space V. Okay, now that we have this definition, we're going to introduce a theorem and another definition for you. Theorem, a span S is basically a subspace of the vector space V. So a span of S is the set of all linear combinations. Those linear combinations form a subspace of V. What's the meaning of that? It means that it is closed under addition and scalar multiplication. So if S, including V1, V2, V3, and Vk, is a set of vectors in a vector space like V, then a span S, which is all possible linear combination of these vectors, is a subspace of V. Moreover, span S is the smallest subspace of V that contains S. In this sense, every other subspace of V that contains S must include all of those linear combinations as well. Now, the definition of linear dependence and linear independence. A set of vectors like S, including V1, V2, V3, Vk, in a vector space V is linearly independent if, when you write the linear combination and set up the equation equal to 0, you only have trivial solutions. What are trivial solutions? C values, C sub i's, must all be equal to 0. Otherwise, we say that, hey, they are linearly dependent. So linearly independent if all of these C becomes 0. Linear dependent, it means that you might end up with at least one non-zero value. Perfect. Example of linearly dependent sets. Consider the following set. The set including 1 and 2, 2 and 4 in the plane is linearly dependent. Why is that? Hey, if I just write linear combination of -2 multiplied by 1 and 2 plus 1 times 2 and 4, this guy becomes 0. So I found C1, which is non-zero, and also this invisible number is 1, C sub 2. So C1, V1 plus C2, V2 is 0, but C1 and C2 are non-zero elements. So these two are linearly dependent. This set, 1 and 0, 0 and 1, -2 and 5, in the plane is linearly dependent. Why is that? I can multiply 2 by 1 and 0. I can multiply -5 by 0 and 1, plus the last vector, which is -2 and 5. So you have 2 plus 0 minus 2, which is 0. Then you have 0 minus 5 plus 5 equal to 0. So again, I found C1, which is non-zero, C2, which is again non-zero, and this invisible number C3 is 1. They are all non-zero entries. They are non-zero numbers. I multiply each one of these by these vectors, and the outcome is equal to 0. So since these are non-zero entries, it means that these vectors are linearly dependent. Another set for you, 0, 0, 1, and 2 is linearly dependent. Why is that? Take a look. 1 times 0 and 0 plus 0 times 1 and 2 is equal to 0. I found C1, which is 1, and C2, which is 0. So I don't have any issue with C2, but C2 is 0. But I have issue with C1. C1 is equal to 1 multiplied by the first vector plus C2, which is 0 times the second vector, gives me 0 back. But C1 is non-zero. So these are all linearly dependent vectors. Testing for linear independence. Determine if the following set is linearly independent or linearly dependent in the space. So the set has vector v1, v2, v3, which are 1, 2, 3, 0, 1, 2, negative 2, 0, and 1. So let us begin, everybody. To test for linear independence or linear dependence, we need to form the linear combination C1, v1 plus C2, v2 plus C3, v3 equals to 0 vector. If all of these CIs become 0, then you have linear independence between them. Otherwise, you say that, hey, they are linearly dependent. So let us begin. C1 times 1, 2, 3 plus C2 times 0, 1, 2 plus C3 times negative 2, 0, and 1 must be equal to 0 vector. So you end up with 0, comma 0, comma 0. Now, you're going to distribute C1 into parentheses, multiply C2 by each component, multiply C3 by each component, and then combine them together. You get C1 minus 2C3, comma, 2C1 plus C2, comma, 3C1 plus 2C2 plus C3 equal to 0, 0, and 0. So two vectors are equal to each other if and only if their corresponding components are equal. You get C1 minus 2C3 equal to 0. The very first components are equal to each other. So this guy is equal to 0 here. And then 2C1 plus C2 is equal to 0, which is this guy here, equals to the 0. And then you have 3C1 plus 2C2 plus C3 equal to 0 as well. So this is your last components that are equal to each other. Very good. Now what? We can form the augmented matrix of this system and then reduce this. So the augmented matrix is 1, which is the component, which is the coefficient of C1, 0, coefficient of C2, negative 2, which is coefficient of C3, and the other side you have all 0 constant. 2 is the coefficient of C1, 1 is the coefficient of C2, and 0 is the coefficient of C3, and you have 0. Then 3 coefficient of C1, 2 coefficient of C2, 1 coefficient of C3 is equal to 0. So you can reduce this. Hey, the pivot must be equal to 1, and everything below 1 must be equal to 0, and the same for this guy here. So let's see. If you reduce this matrix, you get the following identity matrix, and then this guy is equal to 0. What's the meaning of that? It means that C1 must be equal to 0, C2 must be equal to 0, C3 must be equal to 0. So basically found all of those Ci values that are equal to 0. So you basically have trivial solution. It means that all these vectors are linearly independent from each other. Testing for linear independence and linear dependence. Let S be the set of all vectors v1, v2, v3, vk, be a set of all vectors in the vector space like V. To determine if S is linearly independent or linearly dependent, use the steps below. From the vector equation C1, v1 plus C2, v2 plus CK, vk equal to 0, write a system of linear equations in variables C1, C2, and CK. Determine if the system has a unique solution or not. Remember that if your matrix is invertible or non-singular, the determinant of the matrix is non-zero, then you can easily work with the system by multiplying the system by the inverse of A and check to see if you end up with a unique solution or not. If the system has only the trivial solution C1, C2, C3, CK equal to 0, then for sure you can say that S is linearly independent. If the system also has non-trivial solutions, then S is linearly dependent. So these are the steps that you saw in previous examples. This is just a summary. Testing for linear independence. Determine whether the following set of vectors in P2 is linearly independent or linearly dependent. So the very first vector is just a polynomial of degree 2 and less. The second vector is another polynomial of degree 2 and less. The third vector is a polynomial of degree 2 or less. Now, you need to form C1v1 plus C2v2 plus C3v3 and set it equals to 0 vector. So C1 multiplied by 1 plus x minus 2x squared plus C2 multiplied by 2 plus 5x minus x squared plus C3 times x plus x squared. On the right-hand side, you have 0 vector. 0 vector in this vector space is 0 plus 0x plus 0x squared. So every little detail is important. Now, if you distribute C1 into parentheses, you can combine the constant terms. So this guy is C1 plus 2C2. And here you don't have any constant. You only end up with linear term and quadratic term. So you have C1 plus 2C2 must be equal to 0. Then for the second combination, C1 times x plus 5C2x plus C3x, it is equal to 0 as well. So as you can see, you need to combine the coefficients together. These are all linear terms. C1 plus 5C2 plus C3 times x is equal to 0 as well. Finally, you're going to combine the quadratic terms together. Negative 2c1x squared plus negative c2x squared plus c3x squared must be equal to 0. Or if you combine, or if you factor out x squared or combine the coefficients, it is negative c1 minus c2 plus c3, which is equal to 0. So let us begin. C1 plus 2c2 is 0. C1 plus 5c2 plus c3 is 0. Negative 2c1 minus c2 plus c3 is equal to 0. So you have 3 equations and 3 variables. You can easily form the matrix. You have 1, 2, 0, and 0, which are the coefficients of these variables. Your variables now
are CIs. You get 1, 5, 1, 0, and finally you have -2, -1, 1, and 0. You're going to reduce this any method that you feel comfortable. So you have 1, the pivot, everything below 1 must be equal to 0. So you can multiply the first row by -1 and add it to the second row, multiply the first row by 2 and add it to the last row. After doing this, reducing the steps, you end up with this matrix. You have a 1, everything below 1 is equal to 0. You have a 1 here, everything below 1 is 0. And then please note that your last row are all equal to 0. But we need to check these as well. If you form the system of equations, you end up with the following C values. C1 plus 2C2 is equal to 0. C2 plus a third C3 is equal to 0. All right, so you get C1 plus 2C2 equal to 0. C2 plus a third C3 is equal to 0. This implies that the system has infinitely many solutions because you end up with 2 equations and 3 variables. So again, you have C1 plus 2C2. You have to introduce a parameter like t or s. It doesn't matter which one you're using. But since you have a parameter, you end up with infinitely many solutions. And from the second line, you have C2 plus a third C3 equal to 0. You can basically say that, hey, I'm going to take C3 as T and write C2 in terms of C3, which is T. And then since this is written in terms of T, you can write C1 in terms of T as well. So you end up with infinitely many solutions, and the system must have non-trivial solutions, right? That depends on T. And you can conclude that the set S is linearly dependent because you get C values that are not 0. So that's how you show the system has infinitely many solutions or unique solutions and so on. So if you, for example, take one value for t and get your c values, one of the combinations is one of the linear combinations is 2 times the first vector minus 1 the second vector plus 3 times the third vector equal to 0. You can take this guy, anything else. You can take this guy to be, for example, 6 for simplicity. If c3 is equal to 6, then c2 becomes -2. And then here you get C1 minus 4 equal to 0, and this guy becomes 4. So you get another linear combination of V1, V2, V3, which is equal to 0, but these C values are non-zero. So basically show that they are linearly dependent because you found C values that are non-zero, and you can write a polynomial of degree 2 or less as a linear combination of these. And then if you form the linear combination of these and they set it equal to 0, you can find C values that are non-zero. Testing for linear independence. Determine if the set of vectors in the world of 4x1 matrices is linearly independent or dependent. Well, take a look. I have this set V1, V2, V3, and V4, and you have some column matrices. You want to check to see if they are linearly dependent or independent. It doesn't mention anything to find C values or not, but let's take a look at this. What are the steps that we're going to take? From the equation C1 V1 plus C2 V2 plus C3 V3 plus C4 V4 equal to 0, we can rewrite this as C1 times the very first column
matrix, which is your first vector, plus C2 times the second vector, plus C3 plus the third vector, and C4 times the fourth vector. And on the right-hand side, you have the zero vector, which is basically a column matrix. Okay, so let us form the system of linear equations using C values. So basically, you're saying that, hey, C1 plus C2 plus 0 C3 plus 0 C4 is equal to 0. So this is your very first equation. Then you're going to say that, hey, C1 times 0 plus C2 plus 3C3 plus 1 C4 is equal to 0. This is your second equation. The third equation, negative C1 plus 0 C2 plus 1 C3 plus negative 1 C4 is equal to 0. And finally, 0 C1, 2 C2, negative 2 C3, 2 C4 is equal to 0. So we form this system of linear equations. You have 1, 2, 3, 4 equations and 4 variables. If you use Gaussian elimination to show the system how many solutions it end up having, you're going to just see that it only has trivial solutions. How are you going to do that? So let us form this matrix. Shouldn't be that difficult. You have a 1, you have a 0, just basically listing all these entries here. And then here you have 1, you're having the column matrices, and you're going to list all of the entries. Then you have a 0, then you have a 3, 1, and negative 2. Then what else do we have? We have this guy here, which is 0, 1, negative 1, and 2. So if you form the augmented matrix, you end up with 0, and 0, and 0, and 0. Okay, here we go. This is our matrix, right? So if you add the first row and the second row, this guy becomes 0, this guy becomes 1, this guy is 1, and this is negative 1, and this is just 0. And so the rest of these are all 0. Now look at the pivot here, it is 1. If you multiply this guy by negative 1 and add it here, you get 0, you get negative 3, and you get negative 1 here. Then your second row, if you multiply it by negative 1, this guy becomes 0, and this guy is negative 2 now, and this is negative 2. And finally, let us take a look at this guy here. Multiply it by negative 2 and add it here. This guy becomes 0, negative 6, negative 2, get negative 8, then negative 2, and this is equal to 0. So one by one, we get rid of all of these entries. You can divide this guy by negative 2 and make it equals to 1, and then simplify it as much as possible. So basically, after elimination, you're going to see you end up with C1, C2, C3, and everything else equal to just 0. So since you have trivial solutions, it should be linearly independent. So again, for these steps, you should feel comfortable about calculating each step in elementary row operations, or if you want to apply elementary column operations, that's absolutely fine. It doesn't matter which method you're using. So if you want to find the determinant of the matrix here, it doesn't work in this case, all right? What are we seeing here? We have this coefficient matrix. You can only work with a coefficient matrix instead of working with augmented matrix, am I right? So if you find the determinant of that coefficient matrix, if the determinant is non-zero, then you can basically multiply both sides by the inverse of the matrix. And then you have the unique solution. That's the whole goal. So this is what we're looking for. If the determinant is non-zero, so if you find the determinant of this matrix, then you need to multiply left-hand side and right-hand side by the determinant, and you get the unique solution. And hopefully that unique solution is equal to 0. So if the unique solution is equal to 0, then you have trivial solution. It means that this guy is linearly independent. Two vectors like u and v in a vector space V are linearly dependent if and only if one is a scalar multiple of the other one. It's a nice criteria for us, everybody. For example, consider these two vectors, 1, 2, 0, -2, 2, and 1. These two vectors are linearly independent because v1 and v2 are not scalar multiple of each other. For example, you can do the division. You can say that, hey, 1 divided by -2 is not equal to 2 divided by 2. I'm just dividing x components, y components, and z components. 0 divided by 1. So there is no way these fractions are equal to each other. So since these fractions are not equal to each other, it means that they are not linearly dependent. So they are independent from each other. So these two vectors, they are not in the same direction. What about these guys? These guys, 4, -4, -2, -2, 2, and 1. So if you do the division here between the components, for example, 4 divided by -2 is -4 divided by 2, which is basically can be written as, now I'm dividing z values, -2 over 1. These fractions are all equal to each other. All right. So since they are equal to each other, it means that they are linearly dependent. So they are all located on the same line, but in the different directions. So here you have these two vectors, right? They are in this. They are not in the same direction. They are not located on one line, but these vectors, they are all on the same line in the opposite direction. So they are linearly dependent. These are linearly independent. We can basically go back and find C sub 1, C sub 2, and then find those linear combinations and show that for the first one, all of those C sub i's are equal to 0. For these, you can find C sub i's that are non-zero. Prove that the set of vectors is linearly independent. So take a look. You have 1, 1, 1, 1, 1, 0, and you have 1, 0, 0. What are we going to do? We're going to form the matrix, all right? Now this is what you're going to see using the matrices. The matrix in row reduced form can be written as the identity matrix. Now, C1 times 1, 1, 1 plus C2 times 1, 1, 0 plus C3 times 1, 0, 0 is equal to 0, 0, 0. Or basically, since we wrote it in reduced form, it means that C1 is 0, C2 is 0, C3 is 0, and then we are done. These are all linearly independent from each other. The vectors also span the space because the coefficient matrix of the linear system is non-singular. So another piece of information for you. Since you're forming the matrix for the vectors, and this coefficient matrix here is non-singular, you can definitely conclude that these vectors basically span the space. Coefficient matrix is non-singular. It means that you have inverse of the matrix. You can multiply both sides by the inverse of the matrix and find
the unique values for C1, C2, C3 based off of U1, U2, and U3. Or you can take U1, U2, U3 and write them as the combination of C1, C2, C3, and some other values.